It won't be that easy for you to just go away. You will have to think small. No. It's both objectives and theory. So that question is just number one of the of the of the theory. Huh? What? Uh-huh. But why is it an assignment? Okay, so basically, so basically, what we have learned is that what we've learned is using transistors, right, to make logic gates. Simple as that. Now, what do we use logic gates for? So we can combine logic gates in so many forms to produce complex digital systems, right? That's what we're going to look at. Which is known as combinational logic design. So you combine different kind of gates, AND gate, OR gate, whatever, into one complex system, right? And so this is again the end goal of the entire thing. By the time you are done, you should know how to design each of these models, the architecture of each of these models, right? And then what you're going to do is that we're going to use this basic logic gates. You guys know these gates already, and then these are the basics. So just know the truth tables. That's very, very important. Once you know the truth table of each logic gate, everything becomes easier, right? So the first gate is called a buffer. So you see the truth table. So the buffer in an in a digital system, what the buffer does is that it just delays. What the buffer does is that it just delays a signal. So you see that if A is 0, Z is 0. If A is 1, Z is 1. Have you seen it? So it's just the same thing, but it means that what the buffer is doing is delays a signal for you. That's all. Right? So you can see the AND gate truth table, OR gate, XOR. The inverter is the NAND, NOR, XNOR. Just know this truth table and then you are fine. Do you guys know what each truth table is? Like, if I say, give me the truth table of a NOR gate, you guys can easily do that, right? It's supposed to stick in your head. Okay, so now all we are going to look at is how to design a decoder, multiplexer. Then I don't know about the four, I don't know about the other two, right? So now let's look at the first one. What is it? A decoder, right? In digital systems, right? A decoder is just an input pattern detector, right? So what you are doing is that you have some number of inputs, and then for a decoder, so a decoder looks like this. We have inputs, and then we have outputs, some number of outputs. So in a decoder, very important, if you have n inputs, right, the output is 2 to the power n. So the number of output will be 2 to the power n. So if I have n to be 2, if I have 2 inputs here, what will be the outputs? 4. 2 to the power 2, right? Simple. So 4. Understood? So what your decoders do is that so this is the a typical truth table of a 2 to 4 decoder, right? You have 2 inputs, you have 4 outputs. So you have input A0 and I think A1, A0, and then you have outputs Y0, Y1, Y2, Y3, right? So from the truth table, right? Can, can you tell me what it is doing? Just study the truth table a little bit, and then you can actually understand what it is doing. hurry it up, hurry it up. Just what is it doing? Just look at the truth. So the inputs, I have input A1 and A0, right? So if A1 is 0, 0, what happens to the outputs? Just study some pattern. There's a pattern in there. So if A1, A0 is 0, 0, right? Only one of the outputs is activated. So in the decoder, it's like your probably your normal decoders, right? You have so many channels, but you choose one channel. Understood? So here, look at 0, 0. Only one of the output is activated. So it is detecting that if I give it 0, 0, only one output is activated. Understood? So 0, 0, Y0 is activated. So if I give it input 0, 0, Y0 will be activated. All the other Y0 will be activated. All the other outputs will be deactivated. It's as simple as that. If I give it 0, 1, you can see that Y0 is activated, right? The rest are what? Deactivated. If I give it 1, 0, Y2 is activated, and then the rest are deactivated.
Good evening, sir.
Yes, sir.
Please, Mr. Michael came here for a lecture, so he said he wanted to speak to us.
Ah,
Thank you, sir.
so if I give it 1, 1, Y3 is activated, the rest are deactivated. The rest are deactivated. So this is what is known as an input pattern detector, right? Only one output is activated, given a number of inputs, right? Just like your normal decoders, you have so many channels to choose from. You click on one and then only one is chosen. That's how a decoder works. Understood? So now the most important thing is that um, I should know how to use logic gates to design this decoder. So if you know what truth tables are and stuff like that, right? If I give you a truth table, but from the truth table, you should be able to use some logic gates to design the, to to design what the circuit is. Have you guys done that before? Alright, so if I give you this truth table and then I ask you that the first one, if I give you this truth table for the decoder, right, and I ask you to give me the circuit for the first one, just the first line, 0, 0 is supposed to, uh, once I give it input pattern 0, 0, I get y3 is 0, y2 is 0, y1 is 0, and y0 is 0. Can you guys give me the gate? Can you guys draw the gate for that? Ah, what is the gate? The first one, the first line. Yeah. So once you are given a truth table, you should be able to know what circuit it is. So how do you know what circuit it is? Now, if I take my first line, right, I should look at where the output is a 1, right? So it means that input 0, 0, right, we have to pass through a gate, and then that gate, some kind of, it pass through a gate, and then the output of the gate will be a 1. So, and then the output of that gate is Y0, right? So I need to determine what kind of gate it is, right? Now, I can use several gates. I can experiment and use several gates, but once you are experienced enough, all you have to know is that once I use an AND gate here, and then I have input 0, 0, right? And then I take this input 0, 0, and I invert them. This is an inverter. This is an inverter, right? So what happens to my output? So it becomes what? 1, right? Because this passes through the inverter, it becomes 1 here. This one, so there will be 1 here. This passes through the inverter, it becomes 1 here. If you have an AND gate and then the inputs are 1, 1, the output is what? As easy as that. So you have designed your circuit for, I think, Y0. Are you seeing it? Now, to know the circuit for the next line, 0, 1, the same way, right? Take that would be what y1, right? Take your AND gate, right? And then you have one of your inputs is zero. You invert that zero, and then one of your input is a one. You don't do anything to it. So if I have a zero, one here, what happens to my output? It will be one. So I've designed a circuit for the next, and then for the next line, the exact same thing. By two. So one of my inputs is a one. I invert the other input, and then this is 1 0. 1 0 gives me. Are you seeing what is happening? And then the last one is what? Y3. So no, it's as simple as that. And then I can combine. I can do A and B and do some kind of connection to it, and then the circuit is done. It's as that's all there is to it. Do you guys understand?
Yes, sir.
So this is how it looks like. And then once indicators once you have an inverter here, you can decide to make your circuit simple by removing the and I thought it was outside. Hmm? Uh, you are looking for so here the first one was what? So the first one is 0 0, right? Now if I give an AND gate, I want the output to be one. That's my aim. I want my output to be one. So if I put a 0 0 here, right? My output of the AND gate will be zero, but I'm looking for a one. So what do? I have to invert this one. I can only invert this one with another gate called a NOT gate, as I already explained. The NOT gate will invert this one. So if I put a NOT gate here, to invert the zero for me, and then it gives a one. So this is just how the decoder looks like, right? And then you can have several uses of the decoder. Probably one of the uses of the decoder is the I always draw memory like this. I always draw memory, and then within your computers, this is how your memory looks like. It's like this, right? And then you have what is known as the width of the memory, and then you have what is known as the depth. This is how the memory looks like, and then each memory location stores a value. Right? This is how the memory model looks like based on the width. So if my width is 8 bits, right? So this can store 8 bits, 8 bits, 8 bits, 8 bits, right? So and then the depth will now determine how many of those locations are there. As easy as that, right? Now the issue with memory is that once memory is designed like this, you can only read from one location at a time. You cannot read from two locations, right? Only one location at a time. So how do you design a system that can read from one location at a time? Then what you use is the decoder, right? So you see how the decoder activates only one line at a time, right? So if I have a memory that has probably let's say four locations, so location 0, 1, 2, 3, 4, 1, 2, 3, right? So it has only four locations. So how can I design a decoder to address this? I can just use a two input decoder. And then I said that if a decoder has two inputs, the output is what? Four, right? And then it means that I connect one line here, one line here, one line here, one line here. And then based on the inputs, only one line will be selected. So if I give it here a 0 0, so this will be my address. So if I give it a 0 0, only this memory location will be activated, right? So in effect, your decoder can be used to design your addresses to be able to read or write to your memory. That is just one use. And then the another use is It can be used to decode instructions. That one you will see that one later. So now our next one is a multiplexer. Have you guys heard of a multiplexer before? Yeah. So this is how a multiplexer works. If you have so a multiplexer is probably like the opposite of a decoder, but not directly opposite. But because what the multiplexer has only one output and several inputs. So it's like you have how do I put it? It's like it's like you have some one way, right, in which cars can pass through from all directions here. But you know that only one car can pass through, right? Right? So you have only one way because you have only one way and then only one car can pass through. So what the multiplexer does is that it chooses only one car to pass through here, but the cars are coming from different directions. So the cars are your inputs, but the multiplexer allows, or what the multiplexer does, it allows only one signal to pass through, or one, let's say one car to pass through on on a single lane road, something like that. Do you understand? Do you understand? So you have the symbol. I think the symbol looks like this. So if you have a two input decoder, two input, and then you have an output, and then it will allow this one, you have A or B or something like that. And then we have something called the select line, right? So based on this select line, it will allow this one to pass through or this one to pass through. So you usually give here a number, 0 and here 1, something like 0, 1. So if this selector is 0, it will allow the signal to pass through. If this selector is 1, it will allow this one to pass through. But both cannot pass through at the same time. It's impossible, right? So now, if you study this truth table, right, this is a 2 to 1 decoder truth table. Can you guys see, or can you guys understand what is happening in the truth table? What is happening in the truth table? So as I said, there we have a select line, and then the select line chooses which signal to pass through. Here I have two signals, D1 and D0. So that's a two input decoder. It's something like this. D1 and D0. Two input decoder, right? And then this is my select line, this S. This is S. And then the S is allowing either D1 to pass through or D0 to pass through, right? So now look at the S. When S is 0, what happens to the output? Just look at the output. When S is 0, what happens to the output? When S is 0, 0, 0, 0, what happens to the output? And then what is 0, 1? Look at the input also. What is 0, 1, 0, 1? Have you understood? Now look at 1, 1. When S is 1, what happens? What is 0, 0, 1, 1? D1. So you see that based on the select signal, it allows either D1 or D0 to pass through. So if the select signal is 0, it's allowing D1 to pass through. If the select signal is 1, it's allowing D0 to pass through. Easy, right? So if I ask you to draw use logic gates to draw this one, can you do it? Huh? So just so if I say use electric or logic gates to design this truth table, right? Or use the truth table to design some kind of circuits, right? How will you do it? Yeah. Now this is the symbol, but inside I'm talking about the logic gates of the AND gates, OR gates, or whatever that is used to construct it. So just look at it this way, right? I take an AND gate, right? An AND gate. I make one of the inputs is S. So let's say S is zero. What happens? So if S is zero, I invert my S, right? So if S is zero, it is allowing one of the inputs to pass through. What input is it allowing to pass through? Huh? Probably it's what D zero. Right. So I've had, yeah. If S is zero, what is allowed to pass through? D zero. So understood. Now if S is one, what happens? Let's take another S is one. It allows D1 to pass through. Right? Very simple. Then now I want to combine because I have only one output. My output is what? Y. I want only one output, so I can pass this one through an OR gate and I get my Y. Understood? Hmm? Yeah, yeah. You don't know why? Is it?
So that you can get it.
So now, why did I use this AND gate? So that I use an OR gate because you are choosing one of them, and then an OR gate depends on one of the inputs, right? So now, so if here is, so now you know that I can now combine these two S's, right? So now if S is, let's say S is zero here, so what happens? Our signal comes here. This one becomes what? One. Now this same signal comes here. This one is zero. And AND gate, once the one input is zero, the output is automatically zero. Right? Now, but for an AND gate, if one input is a one, the output depends on the other input. Depends on this. So this one will be routed here, this zero, and then the output, and then an OR gate depends on, will depend on this. So it will be this zero. So if S is zero, this zero will be routed through. You see how it is done. Then if S is one, you can pass, you can go to the circuit again and see how it works. Is that easy?
I don't know the secret to this.
Right? The next one is a comparator. So what does a comparator do? So you can compare two numbers, and if the numbers are the same, then you output the one. If they are different, then you output the zero. What gate can I use to do that? Let's just take one bit. So I just want to compare a one bit number, one bit A and B, right? So probably the truth table will look like this: 0, 0, 0, 1, 0, 1. Right. So now, what the comparator is doing is that if they are the same, if the numbers are the same, the output is a one. If the numbers are not the same, the output is a zero. So it means that 0, 0 will give me what? 0, 1 will give me what? 1, 0 will give me what? 1, 1 will give me what? So this is the table. So which gate is this? Which gate repeats this? You, you guys know all the gates, so and and gate per and. An AND gate, what an AND gate does is 1, 0, 0, 0. So it's not an AND gate. Do you guys know what a XOR gate is?
Yes.
So let's take an let's yes. If you use an XOR gate, what happens? There's an XOR gate. What the XOR gate does is that if the inputs are the same, it's a zero. So if the inputs is zero zero, it's a zero. If the inputs are the same, right? So now you can see that this is the opposite of this. Have you seen it? So this is a not XOR gate. Can you say? So this is how an XOR gate looks like. And then if you want a not XOR, easy as that. So you can use that one to compare numbers and then give out a one or a zero if the number is if they're the same or not. Right. So if you're doing four bits, this is how it would look like. You use four of them. Understood? Now the next one is the ALU. So I gave the assignment for the ALU as easy as that. I think I said what I can't remember what. Do some operations with the ALU, right? And huh?
Design a logic circuit from extra inputs ALU to perform the functions in a stable state. Make use of the logic gates together with multiplexers and
Hmm?
decoders. Make use of the logic gates together with multiplexers and decoders. So it will give us 00011011. The function for 00 is A and B. A and B. Then 01 is A or 1 or A or
Huh?
so X or 11 is A equals
Invert that. You invert
Z.
it. So what is the first gate you can use here? So here it means that we are selecting between and or X or and not, right? So we already see what is a multiplexer, right? So I'll have a multiplexer. The multiplexer has what is known as the select lines. So I said the multiplexer has the select lines. So this select lines will be the A. This select line will be the 00, 01, 10, 11. Right? So it will have some 2-bit selectors. We don't have any marker there. And then we have one output, right? Whatever the output is. You have one output. Please let's have a look. So you have the output here. So if 00 is what? And, right? So simple, just an and gate. Just put an and gate here. The AND gate is connected to the 00 line and then it will route that one here. Our next gate is what? OR, right? Put an OR gate here. This is A, B or something. A, B, C. Our next gate is what? XOR gate. Put an XOR gate. Our next gate is what? Oh, uh, it was just supposed to be not B. I just saw it later, but it was too late. So that was a mistake.
Meaning the question
Oh, nah. So it means that the last one is a
the
mistake.
question
That's
is
all.
incorrect.
Oh, massa, massa. So this one
Then I would
is
robot
supposed to
over.
be a not B. All right, so that's how you design your simple ALU, right? Now, this gate is very very important. This gate is what is known as the tri-state buffer, the tri-state buffer gate, and then you saw that all the gates we always have an output for all the gates, and then all the logic we are looking at, we have seen one, we have seen zero, right? Now we have another gate in which you don't want to connect your output to anything, right? So now you have an input. So this is a simple buffer, and then the simple buffer just allows A to pass through without changing it. Now I don't want. I have something called the enable here. So now based on the enable, if the enable is zero, I don't want this output to be a zero or a one. I want it to float. So we call it a Z or or a high impedance or floating. So whatever the value here is, as long as the E here, the enable here is zero, the output is floating. Whether here is one, whether it's zero, it doesn't matter. Whether here is one or zero, it doesn't matter. The output will float as long as E is zero, right? Now, as long as E is one, that's when it will allow the A to flow. That's how the inverter works. Do you understand? And then the inverter is used in a lot of places. Like it can be used in a shared bus. You know that within your computing system, right? You have CPU, you have memory. They are all using a bus, right? The bus is shared, right? But they cannot use the bus at the same time. So one must use the bus and then give the bus to another one to use. So how can you design a system to do that? You can use the simple tri-state buffer. So if the CPU wants to use the bus, it will just enable the gate CPU. You see the top there, the gate CPU there. It will just make it a one, and then it will use the bus. If the CPU don't want to use the bus, it will just make it a zero, and then it can give the bus to the memory or whatever is connected to it. That's simple, right? So this is our last circuit. So now, very important. If you take again in your computer system again, we have a bus, and then the components are connected to the bus. You have your CPU, you have memory, you have probably input output connected to the bus, right? Now, as I said again, this one component can use a bus at a time. So how do you design a circuit to ensure that only one component uses the bus at a time? Now we have something called each line. There's just one type of design. So the CPU, the memory, the IO has a line called the request line, right? We have the memory has a request line to the bus. So request is an input to the bus, then request. So memory has request, CPU has request, memory has request, IO has request line. Now, if the memory or CPU or IO wants to use the bus, it accepts this line, the request line. If I say accept, it means make it one, right? It accepts the line. If it doesn't want to use the bus, it makes it zero. It de-accepts it, right? So if memory wants to use the bus, it makes here one. If CPU wants to use the bus, it makes here one. If I want to use the bus, it makes here one. As simple as that. Then what the bus does is that the bus has what is known as the grant line. All to this, it has a line to the CPU, memory, and IO. So the grant line does is that the bus will look at the request, and then the bus will issue a grant. The grant can be one or zero. If the grant is one, it means that I'm giving you permission to use the bus, right? If the grant is zero, I'm not giving you permission to use the bus. Understood? So now, if CPU requests the bus, so the request is one, and then this is zero, this is zero. Easy. The bus will just grant, we'll just make the grant line here one, and then the CPU will use the bus, and then all the grant lines will be 0, 0, right? What happens if CPU request, memory request, and IO request at the exact same time? What happens? They've all requested, request, the exact same time. What happens? Who or which grant line will be accepted? Will be accepted. Which grant line will the bus give access to? Why? No, this doesn't matter. I can make a memory then yes. So okay, now I've made the memory and I've made a CPU. So which one does it? Right. So what the circuit does is that what this does is that it assigns priority to each device attached to it from the onset. So CPU will have a priority, memory will have a priority, I will have a priority. So the highest priority is of course always the CPU. So it will assign a priority of probably 2 to the CPU, for 1 to the memory, and then 0 to the IO. So uh, if all the request lines are activated, it will give the chance for the CPU to use it as long as it's activated. So we have an issue here, right? As long as it's activated, it will give it a chance. So the CPU can use the bus for like 100 days as long as it's activated. So there are some techniques to avoid it, but that doesn't matter yet. So now this is what it does. So this is the circuit you use as a this circuit is known as the priority circuit, right? And then that is what you use to grant or whatever. So it means that the A3, A2, A1, A0 are your kind of request lines from CPU, memory, or whatever devices. And then your Y3, Y2, Y1, 10 are your grant lines, right? Oh, this is the request lines. The A3 to A0 are the request lines. These request lines. The Y3 to Y0 are the grant lines, right? So based on your inputs, you will grant to either A3, A2, A1, or A0, right? So which one from this table, which one has the highest priority? A3, A2, A1, or A0? A3. Why? Yeah, so it means that it's as simple as that. If A3 is 1, it doesn't matter the other. It is so you see that if A3 is 1, the output, the Y3 is equal to 1. As long as A3 is 1. Which one has the next? Which one has the next? So you see that A2. So if A3 is not 1, that's when A2 comes in. Do you understand? The next one is A0, A1, then A0. So A0 has the lowest priority. So if any of them is 1, it means that the A0 will never work. Right? Yeah, done. Any question? So the homework has been taken. You guys have seen the homeworks already, right? I gave